In this video, we're going to talk about how to find the area between two curves. And what we mean by that is this. Suppose we have some function f, which I've drawn here in blue, and another function g, which I've drawn in red. And suppose that on this interval a to b, the graph of f always lies above the graph of g. So what that means is if x is any point between a and b, then f of x will be greater than or equal to g of x. The question is, how do we find the area that's between these two curves and between x equals a and x equals b? So this area that I've shaded in black. Well, remember that since f is a positive function, its graph lies above the x-axis, the area underneath f, the area of this big region, is just the integral from a to b of f of x dx. And the area underneath the function g, since g is a positive function, the area of this region down here is just the integral from a to b of g of x dx. But notice this black region here, this region that's shaded in black, can be thought of as this big region, the region underneath f, minus this smaller region, the region underneath g. So what that means is that the area that we're looking for, the area of this black region, is the integral from a to b of f of x dx, the area underneath f, minus the integral from a to b of g of x dx, the area underneath g. But let's remember the integral of the difference is equal to the difference of the integrals, so we can rewrite this as a single integral, the integral from a to b of f of x minus g of x dx. And this formula here is the formula that tells us how to find the area between two curves. Now, a couple things I want to point out. Notice the graph of f had to always lie above the graph of g in order to use this formula. So in other words, f of x has to be greater than or equal to g of x for every x in this interval a to b. Now, I guess it doesn't matter what happens out here. The graphs could cross over here or cross over here. But if we want to find this area that's between a and b and use this formula here, the graph of f has to always lie above the graph of g, at least while we're on the interval a to b. Now, another thing I want to point out is that we assumed here that f and g were both positive functions, so we didn't have to deal with things like net signed area. But I do want to point out that this formula works even if f and g are not both always positive functions. So one of them or both of them could dip below the x-axis, and this formula would still work. This formula still applies to find the area between the two curves as long as the graph of f lies above the graph of g. Now, why is that? So suppose we have a situation like this. Here's a graph of f, here's a graph of g. We want to find the area between the two curves. I claim that the same area formula works to find the area between these two curves. So I claim that this, calculating this integral, will still give us the area between these two curves. Now, why is that? And notice it's not as simple as just find the area underneath f and subtract the area underneath g, because these functions dip below the x-axis. What do we mean by area underneath them? Okay, we have to deal with things like net signed area. So I've redrawn the functions here, f and g, and we're trying to find the area of this black region. Notice this point right here is the lowest point on either graph. Maybe it's at a height of, let's say, -4. Well, what I can do is take both graphs and shift them up by at least 4. In fact, let's shift them up by 5. And notice I've done that over here. I've taken the graph of f of x and shifted it up 5. So this is really the graph of f of x plus 5. And same thing with g of x. I've shifted them both up by 5. And notice the area of this region between them, the area of this region that's shaded in black here, will be the same as the area of this region over here. It's just shifted up. But notice now, these are both positive functions. F of x plus 5 and g of x plus 5 are both positive functions. So we can find the area by doing the integral from a to b of f of x plus 5 dx minus the integral from a to b of g of x plus 5 dx. For the same reasoning as before, we look at the area underneath the blue function here, this area, subtract the area underneath the red function, this area down here, and we get this region that's shaded in black. But notice again, the integral of the difference of two functions is equal to the difference of the integrals. So we get the integral from a to b of f of x plus 5 minus g of x plus 5 dx. And notice the plus 5s are going to subtract out, and we're just going to get the integral from a to b of f of x minus g of x dx. And that's the exact same formula that we had before. So the point is, this formula for the area works no matter how these functions are positioned, as long as the graph of f lies above the graph of g on our interval a to b. So here's our theorem. Suppose f and g are functions and that f of x is greater than or equal to g of x for all x in this interval a to b. again, that just means the graph of f lies above the graph of g, then the area of the region that's bounded between the two curves, f of x and g of x, and that's between x equals a and x equals b, is given by this formula. Let's do a couple examples. Find the area of the region that's bounded above by y equals x plus 1, below by y equals 1 over x, and between x equals 2 and x equals 4. So I've drawn the graph here in Desmos, and you can see our top function, y equals x plus 1, the bottom function, y equals 1 over x. So this is like our f of x, and this is like our g of x. And we're between x equals 2 and x equals 4. You could think of these as being vertical lines, x equals 2 and x equals 4. So we're trying to find the area of this green region. Well, notice, according to our formula, the area is going to be the integral from 2 to 4 of the top function, x plus 1, minus the bottom function, 1 over x, dx. If we calculate this integral, that will give us the area of this region. All right, so let's do it. The integral from 2 to 4 of x plus 1 minus 1 over x dx. Now, the integral is going to be, well, we first of all have x squared over 2, and then the integral of 1 is just x. And remember, the integral of 1 over x is natural log of x, or natural log of the absolute value of x. And we're going to evaluate this from 2 to 4. Okay, I'm going to put the whole thing in brackets here. But what this means is we're going to plug in 4 everywhere we see an x and then subtract what we get when we plug in 2. So what we've done here really is we've used the fundamental theorem of calculus. The fundamental theorem of calculus says that the way that we can find this area, this net signed area, is by doing an antiderivative and plugging in the endpoints and subtracting. So we're going to plug in 4. Now when we plug in 4, we're going to get 16 over 2, which is 8, plus 4 minus ln of 4. And then we're going to subtract what we get when we plug in 2. When we plug in 2, we get 2 squared, which is 4, over 2, which is 2, plus 2 minus ln of 2. Okay, now this is really 4 plus 2 is 12. We have 12 minus ln of 4. And then 2 plus 2 is 4, and we're subtracting. So minus 4. And make sure to distribute this negative here. This will be plus ln of 2. So notice 12 minus 4 is 8. And then we have really a plus ln of 2 minus ln of 4. And we could figure this out as a decimal. In fact, we will. But one thing that you could notice is that we can actually rewrite ln of 2 minus ln of 4 as ln of 2 over 4 by the quotient property of logarithms, which is the same thing as 8 plus ln of 0.5, or ln of 1/2. And when I plugged this in a calculator, I got that this is about 7.30685, or about 7.31. Now that's 7.31 square units. In fact, we can go back to Desmos to see if that looks reasonable. Now let me put in the grid here. Notice how many square units are shaded in green. We'll have a full one there, full one, full one. We have 1, 2, 3, 4, 5 full square units, and then we have some partial ones here that looks like a half of one there, half of one there, so that'd be 6. And then we have some partial ones here. Those look like they add up to something a little more than 1. So yeah, something a little more than 7 looks reasonable for the area of this green shaded region. Okay, let's do another example. Find the area of the region bounded between the graphs of y equals x squared minus 3 and y equals 2x plus 5. Now notice here, this one is different because I did not give you an a and a b. I just said find the area that's bounded between these two graphs. So here are the graphs in Desmos. We have y equals 2x plus 5, this linear function. And we have this quadratic, y equals x squared minus 3. And we're trying to find the area of the region that's bounded between these two curves. And notice I've shaded the region there in green. But if we were going to set this up as an integral, how would we do it? What would be our a and what would be our b? Well, what we'd need to do is find the intersection points. Now, the intersection points, it turns out, are at -2 and at 4. So we're actually going to do an integral from -2 to 4. But if I didn't give you the graph in Desmos, how could you find those intersection points, that the x coordinates are -2 and 4? Well, we'll talk about that in a second. But notice, what is the top function here? Well, the top function is 2x plus 5, and the bottom function is x squared minus 3. So the way that we'll find the area is to do the integral from -2 to 4 of the top function, 2x plus 5, minus the bottom function. And you want to make sure you put the bottom function in parentheses here. We're subtracting this whole thing, not just the first term, x squared. So let's go ahead and do this. Well, again, how would we find those intersection points? Well, what we need to do is to set these two formulas equal to each other. We have y equals x squared minus 3, y equals 2x minus 5. We would set x squared minus 3 equal to 2x plus 5 and solve for x. So we're going to bring everything over to the left-hand side. So we're going to have x squared. If we subtract 2x from both sides, we'll have x squared minus 2x. We're going to subtract 5 from both sides. That's going to give us a minus 8 equals 0. And now we solve this by factoring. And the way that this is going to factor is x minus 4 times x plus 2. Notice we have a minus 4x and a plus 2x. That gives us minus 2x. Minus 4 times plus 2 is minus 8. So notice we're going to get 4 and minus 2 are the x coordinates of our intersection points. Now, to find the y coordinates, we could plug in these numbers to find the y coordinates, but the x coordinates are minus 2 and 4. And notice that agrees with our graph. The x coordinates of the intersection points are minus 2 and 4. So we're going to do this integral from minus 2 to 4. So this is the integral that we have. We have the integral from minus 2 to 4 of the top function minus the bottom function. Now, by the way, if you just look at these formulas, how can you tell which is the top one? So suppose I hadn't given you the graphs. Well, one thing you can notice is this is going to be a parabola that opens up, and this is going to be a linear function. So you can kind of visualize how these graphs are going to cross, and you can see that this is the top one. But if you couldn't do that, if you couldn't visualize what the graphs look like, we're trying to find between these 2 points, minus 2 and 4, which one is higher. So you could pick a number that's between minus 2 and 4, let's say 0, and plug it in for x here. Notice here we get 5, and here we get minus 3. So this is above this one. And you can see the point 0, comma 5 there. And this one is 0, comma minus 3. So notice this one is above this. And that would be true for every point between minus 2 and 4. So let's go ahead and actually evaluate this integral. Well, we can simplify it ahead of time. We can write this as the integral from minus 2 to 4. Let's write this in descending order in terms of its the degree of its terms. We have a minus x squared. Notice we have a plus 2x here. We're going to have a plus 5 and a minus 3. That's really going to be a plus 3. So that's a plus 8. Okay, so again, make sure to put this in parentheses so you don't think we have a minus 3. Don't think we have a 5 minus 3. We have 5 minus a negative 3, so that's 8. Okay, so now we're going to use the fundamental theorem of calculus to evaluate this integral. The integral is going to be negative x cubed over 3 plus, well, the integral of 2x is going to be 2x squared over 2 plus 8x, and this is going to be evaluated from minus 2 to 4. Now, we can cancel these 2's if we want here. And so what we're going to do is plug in the 4. And so what we're going to get is 4 cubed, which is 64, and we have a negative out front. So negative 64 over 3 plus 4 squared, which is 16, plus 8 times 4, which is 32. So that's what we get when we plug in 4. Now we're going to subtract what we get when we plug in minus 2. So negative 2 cubed is going to be negative 8, but then we have a minus in front of it. So it's plus 8 thirds. And then when we plug in minus 2 here, it's going to be plus 4. Plug in minus 2 here, it's going to be minus 16. And all of that is in parentheses there. Now, if we simplify, we'll notice we have a negative 64 thirds and another minus 8 thirds. That's going to be negative 72 thirds. And we have a plus, that's 48 here. And we have a minus, well, this is negative 12. So we're going to have a minus negative 12. That's going to be plus 12. This is actually negative 24. We add these together, we get 60, and negative 24 plus 60 is 36. And one of the important things in this whole process is to keep track of all the negatives. Make sure you put parentheses around this. Make sure you keep track of any negatives because that could be an easy place to make a mistake. So our final answer is 36, or 36 square units. And it's always nice to check to see if that looks reasonable. Could this green region have an area of 36 square units? Well, if you draw a rectangle around this, notice that this rectangle goes from minus 2 up to 4, so that length is 6. Then it goes from a height of minus 3 down here up to a height of 13, so that's 16. And 6 times 16 is 96. And so, yeah, the area of this is definitely a little less than half the area of this, and 36 is less than half the area of 96. We could also draw in these grid lines here and count up these boxes and kind of estimate it because they're not all full boxes here. We have some partial boxes. And yeah, that's reasonable that that could be 36 square units. Okay, what about a situation like this where we have the curves that intersect in multiple places and we don't always have a consistent top function, right? Notice on this interval from minus 3 to 8, we don't have one function that's always above the other function. Is there still a way to find the area, the total area of this black shaded region? And there is, and what we need to do is to separate this out into three separate integrals. In fact, what we could do is the integral from -3 to -1 of the top function minus the bottom. Well, the top one there, the blue one, is f. So we'll have f of x minus the bottom function g of x dx. If we use this, that will calculate this area. Then plus, well, what's the area of this region? Well, it'll be the integral from -1 to 4 of the top one. Well, notice the top one this time is g. So this would be g of x minus f of x dx. And then finally, plus, well, what's the area of this region? It'd be the integral from 4 to 8 of the top one minus the bottom one, f of x minus g of x dx. So here we had to break it apart into three separate integrals because at different times, right, meaning on different intervals, we had different functions that were the top function. You always need to do the top minus the bottom. Here the top is f, here the top is g, and then here the top is f again. And what about a situation like this? Notice that f is below the x-axis when we're between a and b. And we just have one curve here, one function f. And we're trying to find what is the area of this region. Well, if we were to just calculate the integral from a to b of f of x dx, that would actually calculate the negative of this area. That would be the negative of the correct answer because notice it's below the x-axis and the definite integral calculates a net signed area. So what we need to do is put a negative in front of this, and that would give us the area of this. Now this negative could either be out here, or you could put it inside here. Okay, the negative is really just the constant, it's -1. That can either come inside or outside the integral. And actually, another way to think about this problem is this actually is a region bounded between two curves, where this is one of the curves. Okay, it's really y equals 0. And this is the bottom curve. So notice, what is the area? Well, it's the integral from a to b of the top function. Now the top function is just 0 minus the bottom function, and the bottom function is our f of x. But notice 0 minus f of x is really just negative f of x. So notice we get the same result, that the integral from a to b of negative f of x dx, that calculates this area. Or this negative can come out in front of the integral as well. So even though it looked like we just had one function here, we could think of this region as being bounded between two curves. The first curve is y equals 0, which is the x-axis, and the bottom curve is our f of x.